sniffing out concealed nuclear weapons with cosmic rays for two reasons. One of them, it's catchy, no? How many of you came because of that? And the second reason is, don't you hate it when you click on something on YouTube or WhatsApp that sounds too good to be true? Like, for example, a month ago, there was this planetary alignment. You could see all 5 planets in a row, and you won't see it again in another billion years, that sort of thing. Or the moon's going to be the closest it's ever been. It's like this size. Worse than that, I got a WhatsApp message from colleagues of mine that said that last year there was a solar storm, massive solar storm. So there was all this northern lights, aurora lights that you can see, very intense. In fact, I got a WhatsApp that showed Uppington showing the southern lights, bright and pink and purple. Luckily, I had a colleague that's got family in Uppington that said, no such thing. No such southern lights in Uppington. This is actually true. This is actually true. I kid you not. So I thought I'll take a long route to get to this answer. You're being bombarded by muons as you're sitting there. There's about 10,000 muons that's hitting your body every minute. Whether you knew it or liked it or not. In fact, hold out your hand like this. You're just getting about 1 muon a second going through your hand. How does it feel? It hurts a little bit. So we are being bombarded by these cascades of muons, and they have their origin at the top of the atmosphere. I brought a little demo along. It's this little box. It's actually 2 little boxes. I feel a bit stupid about this. This is a muon detector, but it's the slowest demonstration and the most boring demonstration I've ever done in front of a class, because at the rate the muons are hitting this detector, we're going to wait forever to see something on the screen. So I've got some slides showing the rates here that I'll pop up in a moment. But let me just explain to you what this is. Some of you might find this interesting. There's actually 2 detectors, one in each of these boxes. It consists of a piece of plastic. It's called a scintillator. It's a plastic that will fluorescence when ionizing radiation goes through it. And there's a little photodiode at the bottom that picks up that flash of light, converts it into a signal. We've got some electronics there. Got an Arduino development computer there at the bottom that just transfers that data into a bunch of information that I can send to a computer or so. And then it displays it here on the screen. Now, what you can see from this demo, really exciting demo, is every time a muon goes through one of the detectors, the LED will flash. And the top LED will flash more than the bottom LED because these 2 detectors are positioned, as you can see there in the top left, back to back. The plastic scintillator is close to the other detector's plastic scintillator. I've connected the 2 detectors together so that the 2 detectors are what we call in coincidence. In other words, the bottom detector will only fire when the top detector fired, saw something, and the bottom one saw something. The top one will fire all the time a muon goes through it, but the bottom one will only fire when something triggered the top and the bottom, to insist that this is not ambient radiation hitting the detector on the sides. So this is something that has to come through at the top, and if you look very carefully, the top one will blink, and the bottom one, now that you're looking at it, won't blink. Did it? Okay. and so I can tell you the rates of this on the next slide. So on the left side are the rates when the detector is positioned like this, and the bottom detector is showing me a rate of about 0.25 muons per second through this small little detector. Now, interesting about this, if I turn the detector sideways, and again, it's very difficult to see, the top one will still fire, the bottom one will even fire less. Because most of the muons are coming from above, from the zenith angle. In fact, there's a distribution, a cosine, your trigonometry from school, there's a cosine square distribution because the muons coming from the sides have to go through a thicker piece of atmosphere than the ones from the zenith angle. So there should actually be very little muons coming in on the sides. And the figure here on the right shows you a much lower rate. There's still some triggers happening on this small detector. There's some electronic noise. But you can see the rates are much less. So this is a muon telescope. It's actual muon telescope, and it shows you actually the rates on the front. And afterwards, you're welcome to come and have a look and play with this if you want to. And the nice thing about this is if you get bored with my voice, you can just stare at this thing. Really exciting. We actually have a bigger muon detector than this. This is a toy. This is done by MIT students, but it's a toy. We've got currently one in the Huguenot Tunnel. That's about 1 meter by 1 meter by 1 meter. And it's measuring muons coming through the overburden of this mountain. There's the peak of the mountain. This is the Tweeskloof Tunnel. That's the Parel entrance. This is the Worcester entrance on the right. Here at the bottom, you can see the typical photographs that everybody sees. So in the middle of the picture is the entrance and the exit of what they call the South Bore. That's the tunnel that everybody's using. But if you look to the side there on the left, there's another entrance. And that tunnel, most of you probably know about this, but in the 80s when they dug this tunnel, they dug 2 tunnels. So there's a North Bore that's not furnished. You can drive through there, but it's not a tar road or anything. And we've currently got the detector in that service tunnel. So here's a couple of photographs that shows where I placed the detector. And I personally placed this detector at different positions. I've placed it at several positions along the tunnel just to see what the muons do when they go through the overburden. And you can see the mountain is quite large there at the maximum overburden. It's about 800 meters of rock, granite, and sandstone. When you come to this side, it's much less. So less absorption of these muons. And you can measure them. Of course, again, you're actually trying to see nothing because the idea is that the overburden will shield the detector from muons. So you can see some photographs of the tunnel there. You can see on the very right is a picture of the tunnel. I took my dad there. This is my dad, by the way. I took my dad there to accompany me the other day. So a few people have been in that tunnel. It's a selective group. If you email me, we can make a plan. But I've placed the detector at these different positions. I'd just like to show you some of these results just to give you a little bit of a taste. The reason why we have this detector, it's on loan from France, but we are starting a project called the PAUL project. PAUL stands for the Parel Africa Underground Lab. It's an initiative to create a Southern African or Southern Hemisphere underground lab designed for low radiation measurements. Because everybody now is looking for that elusive dark matter particle, the thing that we don't know what it is, how to measure it, and it doesn't really interact. But we need a very quiet environment for that. So we go underground, shield us from all these muons. And this is a sort of a design plan. This is a lab in Spain, the Canfranc lab, on which we will build the design. And at the end of the day, you can see there in the top photograph, there's a little picture showing where that lab is going to be. So we're going to put it in the current South Bore. Sunrail is going to change that tunnel so that the North Bore becomes the one way that goes to the west, to the east, and then the current carriageway is going to be the one from the east to the west. And that's the plan for the future. And this detector that I've planted there in the tunnel, it's basically an enlarged version of the small little detector. It's got scintillator plates, and these scintillator plates will flash light when ionizing radiation goes through it. In fact, this one's got 3 planes to ensure that we really measure muon events and not just ambient radiation. And you have to trigger all 3 of these plates to be able to justify that it's a muon. And then there's some signal processing that we do. In fact, this is quite a sophisticated detector. It's made of scintillator strips. Each strip has an optic fiber in it to collect all of that fluorescent light, and then takes it to what we call a photomultiplier tube, some photosensor that will count the light, and then it will give us all these signals. It's on loan from France. I've placed it in the tunnel now at about 5 or 6 positions. It's going to go back at the end of the month, and then we're done. I had it at Stellenbosch University. Here the detector is standing in the quad in Stellenbosch, and we're measuring what we call an open air measurement. I just want to see what the muon flux is there in the quad. And the rates were actually quite tremendous. We measured about 50,000 detector events per day. 50,000 detector events. I'm calling it detector events because there's some deficiency in the detector anyway. But these are coincidence events. That's probably Most of the time, they're muons. And here you can see what we call a heat pattern. So the very bright yellow are where a lot of muons hit, and the ones on the sides that more blue, that's fewer muons. And the ones on the side come in at different angles away from the zenith angle, and the very center, that's the zenith angle. And so there you've got this distribution of muons from different angles. So this is about 300 muons every 10 minutes in open air. When we take this into the tunnel, in the center of the tunnel, that's what we get. About 100 counts in 50 days. That's about 2 muons going through that detector per day. And what I've done, so you can see where it's positioned at what we call vehicle crossing 2. It's in the middle of the tunnel. The tunnel is a 4-kilometer tunnel. We're in 2 kilometers. And I've put a little circle around to let your eye see where the symmetry line is of a distribution that's isotropic. And you can see it's slightly asymmetric. There seems to be more counts on this side than on the other side. Can you see why? That overburden has a slope. And so more muons can penetrate from the right to the detector in that yellow cone than from the other side. And you can actually see that. In fact, when we moved the detector to the other side of the maximum overburden, we saw the exact opposite picture. Isn't that nice? So this was positioned at about 1,500 meters from the entrance on the parallel side. Here's my detector again. Here's that heat pattern that I told you about. And you can see much more muons coming in from the left than from the right, as you can see that massive slope there. That cross-section of the mountain, this is an old article that was published in the late 80s, but it shows that there's about a half a granite level and a half a sandstone level, and that's going to affect the amount of absorption of these muons. I always put this photograph on because I'm quite proud of my antennas. To get a Wi-Fi signal to this detector, I need an antenna that can, run through the tunnel without wires. So if you ever want to put your telescope somewhere out in the field and you need Wi-Fi internet, you've got these nano beams. So this one is sending a Wi-Fi signal down the tunnel, as you can see, and it allows us to remotely operate this detector. Now, unfortunately, this was 84 days, 300 events. The statistics are super low. So it's very hard for us to do any judgment on the composition of the mountain over this short time. But of course, these underground labs have other purposes besides the fact that it allows us to study sensitive detectors and how they operate. They actually use these muon telescopes to look at volcanoes. So if you're interested in volcanoes and the dynamics of the inside of these rocks, you would take this muon telescope and observe that mountain over a lot of time. And as the muons go through the mountain, they free. And they go through the mountain, you can actually see the dynamic density changes on the inside of the mountain. So this is being used a lot, and the Jacques Moteau, the French man who is part of the design of that detector, is shown there in the photograph. He's taken this all across the world to different mountains. But these underground labs are especially useful for low activity counting. They look at ice samples, for example, and they measure the cesium, the radioactive cesium inside. And for that, you need a very quiet environment. You don't want to be bombarded by other signals. So you need an underground lab. You need an underground lab to do biological studies, to see what the effect is of radiation on cells and organisms, or electronics for that matter. And then, of course, this whole idea of dark matter. The idea about dark matter is that whatever it is and however it interacts, it may produce known particles like neutrinos as secondary particles, like muons as secondary particles, and we could detect those secondary particles and then infer what these dark matter particles were. So in these underground labs, you have these massive water neutron and neutrino detectors that will measure these very rare neutrino events. And again, you need shielding from muons, which are making it to the surface of the Earth. And so there's also this thing of looking at astronomical processes, cosmic processes like what they call blazars. You've heard of blazars? So a quasar that has got this jet coming out in one direction. And together with a burst of radiation from that quasar, you can also measure neutrinos. And the two in coincidence will tell you something about that event. And so this is super important astrophysics to connect underground lab measurements of neutrinos and muons with things like SKA, where we've got other wavelength telescopes looking at these events. And of course, in these underground labs, we will use this muon detector to shield us, or at least cancel out the signals from muons, and to see what is actually happening inside these detectors. They also help us to study the functioning of very sensitive CCD chips that they use in astronomy and telescopes. So there's a good motivation for South Africa to invest in this underground lab. We'll be one of about 3 underground labs in the Southern Hemisphere. And that's very important. There is some seasonality to dark matter, apparently. So the idea is that as the Earth and the Sun and the solar system moves through the galactic material that contains maybe the dark matter, when it goes one way around the dark matter and comes back at another time of the year, so there's the 6-month cycle, that in some points you'll get more of the dark matter interaction and less of the dark matter interaction. So there's this seasonality that we want to test to see if the northern and the southern hemisphere sees the same flux. So there's a lot of reasons for us to invest in this kind of detector. Okay, let me take you to school. Remember this, your standard model? So the standard model, what is a muon? I've spoken a lot about muons. Nobody raised their hand and said, but what is a, you want to ask? So if you forget anything I said, just remember that a muon is what I call a bloated electron. It's an electron. It is a fundamental particle. You can't break it up. It's part of the family of particles that we call leptons. They're the ones that are in the green. They're the ones you can't break up. They're the electrons, the taus, the muons, the neutrinos, because every lepton, like the electron, has a neutrino associated with it that comes with the decay. For the muon, there's a muon neutrino. For the tau, there's a tau neutrino. And each one of these leptons have an antiparticle, which is the same particle but opposite spin. So electron, you know, has got a negative spin. The anti-electron or positron will have a positive spin, a positive charge. Muon, you get a positive and a negative muon, and they each have their own neutrino and the tau particle as well. So these are fundamental particles. You can't break them up. They are different to the quark constituents. They are different from things that are built up by quarks, the building blocks of protons and neutrons, baryons, hadrons. We'll talk about that in a moment. So a muon is this fat electron. It weighs about 200 times more than an electron, and we often describe its mass in terms of an energy unit, MeV, mega electron volt. I don't know if that's familiar to you, but an MeV is just a compound form of energy. 1 electron volt is a small amount of joules. It's like 1 times 10 to the power of minus 19 joules. It's a minuscule amount of energy. It's the amount of energy that when you take an electron and you move it over a 1 volt battery and you let it go, it's got 1 volt of energy or 1 electron volt of energy. So that's a small amount of joules, minuscule. So in terms of MeV, we're going to talk about 105 MeV mass, and that compares to an electron. That Me there on the third point is the mass of an electron, half a MeV. So half a MeV for an electron, 106 for a muon. Protons and neutrons in the order of a GeV, so about 1,000 MeV for proton and neutrons. And I want to highlight protons and neutrons because there are what we call meson particles that interact between protons and neutrons. And the muon is not that. Come to that in a moment. So muons, where do they come from? They're produced by the decay of ions. Are you with me now? It's electrons, muons, pions, leptons, baryons, mesons. I know Johan is already dreading the test I'm going to have at the end. I'll come back to this. I just want to introduce some terms because I'm going to come back to it in a moment. So pions are produced high in the atmosphere. Pions are mesons. They are made up of quarks. They are formed when cosmic rays like energetic protons hit the upper atmosphere. They hit the molecules. They produce these 2 quark particles called pions. And the pions don't live very long. They live for about a few nanoseconds and then they break up. And one of the products are these muons. So muons are secondary particles coming from the decay of pions, which are formed by cosmic rays slamming into our atmosphere, the molecules of the atmosphere. And I've got an equation there if you like this kind of thing. So the pion decays into a muon plus a neutrino for that muon. Some history. I love the history. You know that I'm a nuclear physicist. My field is 120 years old. 120 years ago, Rutherford discovered the nucleus of a nucleus. Only 120 years ago. That's the previous century. It's not long ago. So there was a guy, this is a Japanese scientist with the name of Yukawa, in the 1930s. He predicted the existence of a messenger particle called a meson that will carry the information of the strong nuclear force. So, there's no such thing as a gravity field. You know that Einstein says that the limit in speed is the speed of light, 3 times 10 to the power of 8 meters per second. Nothing can move faster, not information, not particles, not light. So how does Pluto know about the sun's gravity? Because that information about that force needs to travel 40 light years or wherever, 40 astronomical units to Pluto. You know that the sun is about 8 light minutes from us. That means light at the speed of light will take 8 minutes to reach us. Yukawa said, okay, but here's the thing. Since nothing can move faster than the speed of light, gravity, that force field, can only travel at the speed of light. And so that means if the Earth is going around the sun and light takes 8 minutes, and therefore the message of gravity takes 8 minutes, that means if the sun should blow up, the Earth will keep on orbiting for another 8 minutes before it realizes there's no more attraction and I need to fly off at a tangent. And so Yukawa said, well, all forces in nature is really the exchange of a messenger particle. And the messenger particle for the strong nuclear force that holds a nuclei together, the protons and neutrons, is this meson particle. He predicted the mass of the muon to be about of this meson to be about 131 MeV. There's a nice little equation using Einstein's equation to derive this. He's basically saying that if the message between a proton and a neutron can move at the maximum speed of the speed of light, and the range of the strong force is about 1 femtometer. It's a small little force. Further than that, they don't feel one another anymore. If that's the limit to the range of that force, and it can only travel at the speed of light, maximum, then the mass or the energy of that particle must be about 131 mega electron volt. And so when they did discover the muon in the 30s, this was Anderson and Neddermeyer in the 1937. They've got an article there that I showed you. When they discovered the muon in their cloud chambers, the tracks it was leaving, they thought, we found Yukawa's meson, the thing that mediates the strong force. In fact, I took this extract from that physical review paper. They said that there exists particles of unit charge, plus or minus 1, but with a mass larger than that of the normal free electron and much smaller than that of a proton. That's what they wrote when they discovered it for the first time. However, later they found that the muon is not interacting with protons and neutrons. It doesn't feel the proton and neutrons present. It can't be that mediated particle. And so when the pion eventually was discovered in 1947, that's World War II. When the pion was finally discovered, they realized, okay, that's the Yukawa meson. So muon had a long route. In fact, they first called it the mu meson, thinking it was Yukawa's meson. That mu stuck, so we still call it the muon, but it's not a mu meson. The word pion means pi meson, and that's why pion still sticks. But muon still stays with us. However, it's not a meson, it's a lepton. It's a fundamental particle. It doesn't interact with protons and neutrons. It's very weakly interacting. As I said, muons are formed high in the atmosphere. They form at the edge of the atmosphere about 15, 16 kilometers up. And they decay very quickly. They take about 2.2 microseconds to live, and then they die. Then they fall apart. They fall apart in electrons and neutrinos again. And yet we see them. 16 kilometers later, we see them on the surface of the Earth. And so this is a conundrum. If you just do a quick calculation in your head, I know your guys are still sharp. So take 2.2 microseconds moving at the speed of light. How far can you get? Well, it's about, you don't have to do this, it's about a few hundred meters that the muon can actually classically move before it decays. Derek, you were mentioning that to me when we started. So that's a problem. How do they make the 15, 16 kilometer distance? Well, this is where Einstein suggested that when you move at these, what we call relativistic speeds, these fast moving small particles, then you need to take into account special relativity. And that's where, if you look at the muon from his reference frame, he lives 2.2 microseconds, but the distance that he has to travel is much shorter than 16 kilometers. That's only about a few hundred meters, according to his reference frame. We call it length contraction. And for us as observers seeing this muon come down, we're not seeing its actual 2.2 microsecond lifetime. We see its heartbeat much slower, about 80 times, 40 times slower. And so that slower measurement of his heartbeat for us allows us to measure a longer distance. And we actually observe it here. So this is also proof of Einstein's special relativity. You need to take into account the speed of light when you do measurements of position and time. So now we see all these muons at the Earth's surface. We get about 10,000 muons per square meter per minute hitting the surface of the Earth. And what can we do with those? Well, we can use them as X-rays, or so I should call them muon rays, and we can make muon scans, like they did, for example, with the Great Pyramid. So depending on the density of the material these muons have to go through, they will lose energy, and we can make scans. We can put a muon detector next to the pyramid and look for voids or density voids or increased rock density. So in 2017, 3 labs got together in Egypt, and they did this scan pyramid project. You can Google this. There's some YouTube documentaries about this. I think there was a Netflix documentary about the scan pyramid project. 3 groups got together, each one of a different type of muon detector. There was a Japanese group that made these emulsion films that left tracks when the muons hit them, and they placed these emulsion strips underneath the king's chamber in the queen's chamber, just below that grand gallery of the pyramid, looking up. So they were observing muons coming through the whole of the pyramid and hitting through all the voids, hitting that queen's chamber. There was another group that had a scintillator telescope there in the middle picture. Again, scintillators just like my detector here, and it was also looking up, basically in the same position as the emulsion films, seeing what the flux is of the muons. And then there was another group that had these gas electron multiplier detectors. They placed outside of the pyramid and looked at the muon flux through the pyramid on the side. And they correlated their results. And I think this is fascinating. So what the muon detectors on the inside would see is the view from below, looking at muons coming through. And you can see the pyramid, of course, is quite dense at the middle and then less dense on the sides. And then this one muon detector on the side was positioned next to the detector, next to the pyramid, and looked sideways at the flux through it. Here's the results. This was beautiful. So the picture on the top left, those are the actual muon counts. Now remember my picture that I showed for the open sky measurement at Stellenbosch University, that heat pattern? Well, there's the heat pattern. You can see it's very blue in the middle. That's the densest part, so no muons come through there because that's the thicker part of the pyramid. And the sides, they are less dense, so you get a lot of muons coming through. It's very red there. But what you need to see, and I don't know if my mouse is going to pick this up. This mouse is very small. Let's see if I can have a laser pointer here. Derek, I don't know if this is going to be visible on the... So if you look at the top here, there's 2 lines coming down, one next to one another. It says on the left is new void, and on the right it says B. If you compare that to the picture next to it on the right, that's a simulation. That's a computer code running a simulation. If we know what the inside of the pyramid looks like and we simulate muons coming through with some random processes, that's the picture we should see on the right. And if you compare the two, you can see there's a little bit of an extra density line there, locus there visible, right there where my cursor is going up and down. And so one experiment, this is the emulsion film, suggests that there's something there of low density that's not absorbing the muons. They did the same with the scintillators, and they got the same results. Very difficult to see, but you can see the data in that strip there. There's a bump there showing an increase in muon flux. And then very quickly, the scan from the side, and if you look at that top left image, again, that's my open sky measurement, but you can see the shadow of the pyramid as it's blocking the muons. And what they did is they carefully looked at all the sections of that image to see if there's any sort of, say, impurities. And they found small little bumps that's not part of the regular density distribution. And this is a third measurement from the side collaborating what they saw on the inside. And so I think this is public knowledge that there's a void above the Grand Gallery, about the size of the Grand Gallery. And I think the Egyptologists there agreed, except they don't want to bore into things or anything. So this is a beautiful thing. Non-invasive free muons, and you can see an X-ray or muon ray image of things like the pyramid. In fact, when the Fukushima reactor burned out in the 2011s, what they did is the team got together and they had a muon detector that they positioned on the side of the reactor, and they were looking at muons coming through the very dense materials. The nuclear fuel, uraniums, plutoniums, these very heavy metals, very absorbing. And what they did is they compared their muon scans with simulations. So this heat map that you see there on the left, that's a simulation again. Using what they know of the construction of that reactor. And what they were looking for is the storage of the fuel rods. Were they still where they're supposed to be, or did they burn through and drop to the ground? Because that affects how they decommission the system. And so they actually did find that the heavy metals drop down and they're not where they're supposed to be. So this is tremendously important for us to be able to make scans of things where you don't want to send people in. And I thought you're going to like this. So you've got these supernova remnants. There's two of them there at the top. This is supernova W44 on the left, and this is IC44-3. Some of you may recognize this. This is called the Jellyfish Nebula. It's in Gemini. And what they did is they had gamma ray and X-ray telescopes in satellites looking at these nebula, comparing it with visible observations, and they saw a lot of bombardment of gamma rays coming from these events, these remnants. So that means there's some sort of shock wave or some sort of accelerant that's pushing out a lot of cosmic matter, like protons and hadrons and pions. And when these pions decay, they form muons and gamma rays. And these gamma rays that we pick up in outer space looking at these supernova remnants must tell us something about the mechanism of these explosions. And so this is a multi-wavelength picture of that jellyfish nebula, and the bottom graphs are gamma ray flux as a function of the energy of the gamma rays, the frequency of the gamma rays, if you want. So this is amazing what we can do with the connection between terrestrial muons, gamma rays that we measure with gamma ray telescopes, and cosmic events. I thought you'd like this, so I took a stellarium screenshot of the region that you all recognize. Orion, you see Orion? Yes. So there's Orion, the belt of Orion. This is meant for us, southern hemisphere, so Orion's upside down. There's Taurus, the bull in the bottom left. And then here's the Milky Way. Sorry. Here's the Milky Way. And then here, Gemini is somewhere here. The constellation Gemini is somewhere here. I think this star here where the cursor is, that's the third brightest Gemini constellation star. If I zoom in that region, and I zoom it here on the left, you'll see there's some fuzzy spots there. There's a top nebula. I don't know what that is. But there's a bottom fuzzy spot here next to that Gemini third magnitude star. And that's the Jellyfish Nebula. Is that Monkey Head? All right, that's Monkey Head. So this is Southern Hemisphere jewel boxes stuff here. This is what we can see if Orion's up. So next time you go out, have a look here. I don't know how long you have to time exposure to be able to see this, but I zoomed into that Jellyfish Nebula. IC44. And there's a bigger picture on the right. And here's astrophotography done by, I think, Susan Weber did that. And you can see the nice picture of the different chemicals in that picture. So that one is emitting gamma rays. Massive gamma rays must come from ion decay. Okay, now that we have this nice tool, we can use this tool as a sort of a scanner, and we can measure things just like we use CAT scans and MRIs and X-rays to look through the human body. We can also look through other things like cars and trucks and see what the density composition is. And that forms the idea of muon tomography. So there's two ways of doing muon tomography. There's the one that I'm showing here. We just on the left showing you how muons are coming through something and looking at the muon flux using a detector. Or we can put a muon detector in front and behind the substance, the object, and see what the scattering angles are of the muons before and after the absorber. And very dense, high atomic number substances like uranium, plutonium, tungsten, and those things tend to scatter muons very much more than ions and tins and lower mass, lower density substances. So using that information, we can measure what we call the radiation length, the penetrating depth through different materials. And this just shows what some of the research labs are doing. In the middle picture there, they've got a setup with different blocks of metal. That's a block of lead there in the top left, tungsten in the top right, uranium in the middle, tin at the bottom left, and iron in the bottom right. And on the right figure is the hit pattern or the density distribution of what they measure. And you'll notice there in the middle that the uranium is much more dense in the picture. That means that the scattering is more severe, indicating a very large atomic number element, other than lead or anything like that. The idea here is then you can now bury or conceal heavy metals like uranium, plutonium, even in a lead container to shield radiation so that radiation detectors at the border don't pick them up. But this muon scanner will, because the muon scanner sees right through the lead and looks at the very intense scattering of muons through dense, high atomic number substances like uranium. So, as I said from the beginning, we can do this. So you build a very big muon detector. It consists of a detector above and below a truckway. You let the truck go through, and you measure these muons as they come through. And these are massive detectors. You've got one at the top and the bottom, and so you don't need that much big of a flux. You don't have to wait like I'm waiting here forever. By the way, some of you have had eyes that start going here. So the muon flux is 0.2 at the moment. If I'm holding it up like this, 0.2. So I'm going to put it on the side, and I'll show you as we end. So the idea is that we can start designing muon detectors to be used in industry. Here's another lab. This is at CERN, where they've got, in the bottom picture, they've got some heavy metal word written out with letters, and they look at the muon absorption using these, what they call gas electron multipliers. It's a gas chamber, and they look at the ionization of that gas. It gives you a cascade, and they measure the signal coming out of that. So we're developing detectors to be able to do this for us more accurately. I want to end with this slide. In the 1930s, we had these bubble chamber tracks showing odd new particles that behave differently coming from outer space. They were atmospheric showers. Since then, and by the way, that picture there on the left is a bubble chamber showing a track of a muon going through a sheet of lead. There's a sheet of lead in the bubble chamber. It's that bar there, horizontal bar in the middle. And the muon track goes straight through, and then there's a magnetic field, so because it's charged, it will bend its path. We've come from that in the 1930s to our most modern experiments at the Large Hadron Collider in Switzerland. And this is called the CMS. It's the compact muon solenoid. It's a 2-story high solenoid measuring muons in the search for dark matter. I want to end here. Thank you. The rate is now